Hi, this is Roopa Prasad, Assistant Professor, Department of Computer Applications, MITS College. So today we are going to discuss about the topic called as secure hash function. So in this secure hash function, we are going to discuss about the SHA algorithm, that is secure hash algorithm. That's what we are going to discuss. Now coming to the contents of this presentation. So first we are going to discuss about the introduction part, then we come for the secure hash algorithm. So in this particular one, we are going to discuss about SHA-512, and we are going to check the what are the processing steps of this SHA-512. Then we go for the processing of a single 1024-bit block. Then we discuss about the behavior of secure hash function. Then we go for the SHA-512 round function. Then finally we go for the creation of 80-word input sequence for SHA-512. So coming to the introduction part. So this secure hash algorithm. So the topic what we are going to discuss is secure hash algorithm. So it is most widely used hash function. So what is a hash function? Hash function is one of the message authentication function which is going to ensure the integrity and also the authentication of the message. Okay, for this hash function, the most popularly used algorithm is a secure hash algorithm, and this SHA was published by NIST, and it is published as a Federal Information Processing Standard in 1993. Okay, so first SHA was published in 1993. Later, there are some weaknesses, some flaws are there in SHA, and we term that is known as SHA 0. Okay, and there are some flaws are there in the algorithm. So this algorithm has been revised and it has been renamed as SHA-1. Okay, under the name called as a FIPS 181 in 1995. Okay, after even though there are some flaws are there, so the after that it has been revised in 2002 and it has been named as SHA-2. Okay, so this SHA-1 is going to produce a hash value of 160 bits, whereas this SHA-2. In SHA-2 we have three variations. One is a hash value of 256 bit, and one is the hash value of 384, and one is the value of 512. So they are called according to their the hash values. One is called as SHA-256, and the one is called as SHA-384, and the one is called SHA-512. Okay, all these are collectively grouped under the algorithm called as a SHA-2. Okay, so actually this SHA algorithm has been published in the year 1993 and it is termed referred as SHA-0. After in 1995, that SHA-0 has been revised and it has been referred as SHA-1, which is going to produce a hash value of 160 bits. Later in 2002, this has been again revised, and it has three versions. One is called as a SHA-256, that is, the algorithm is going to produce output of 256 bits, and this algorithm is going to produce output of 384 bits, and this algorithm is going to produce a 512 bits, and these three versions are collectively called as SHA-2. And later in 2008 another version, that is 224-bit version, has been added. Okay, so in 2015 two additional algorithms are added to the SHA. One we call it as SHA-512-224 and another one is called as SHA-512-256. These are the two algorithms that has been added to the SHA in 2015. Okay, and this SHA-1 and SHA-2 also specified in RFC 6234, which essentially duplicates the material in FIPS 183 but adds a C code implementation. That's a brief introduction of SHA, how it has been published, that all the information is this. Okay, so actually SHA is a secure hash algorithm which is a most popular hash function. So first it was published in 1993, later it has been revised in 1995, and later it has been revised in 2002, then in 2008, and finally in 2015. So coming to this SHA algorithm, so here in this presentation we will discuss about 512, that is it belongs to SHA-2. SHA-2. We are going to discuss about particular 512 and remaining will be similar to this 512. So we are going to discuss about this algorithm that we call it as a SHA-512. SHA-512, that is secure hash algorithm 512. Okay, so this algorithm is going to take a message of maximum length less than 2 power 128 bits. Okay, so generally hash function, what is the main importance of hash function? It takes a variable size input and it gives the fixed size output. This particular SHA-512 algorithm is going to take the variable size of input. This input should be maximum. What is the maximum length of the messages? It should be less than 2 power 128 bits. Okay, and this algorithm is going to produce 512-bit message digest, that is called as a hash value. Okay, it is going to give an output of fixed size, that is called as a 512. The message will be of variable length, but the output of fixed size. It is going to give a fixed size output of size 112-bit, which is a hash value, or we can call it as a hash code, or we can call it as a message digest. Anything is okay. Okay, and this SHA-512 insists the length of the original message must be less than 2 power 128 bits. Okay, there is a one requirement for the SHA-12. The message can be of variable size. Variable size in the sense it can be of any length, but the length should be less than or equal to 2 to the power of 128 bits. That is a main restriction that is going to apply in the SHA-512. Okay, and this input message is processed in 1024 bit blocks. Okay, so the message is divided into blocks of size 1024 bits. Okay, so the input is processed in 1024 bit blocks. And here we are going to discuss about the processing steps of SHA-512, how we are going to process this algorithm. So first we have to consider about the length field and padding. Okay, so what is a length field and padding means the input for this algorithm is a variable length message, but what is the restriction? It should be less than 2 power 128 bits. Okay, and it is going to produce fixed length output, that is of 512 bits. So before we are going to produce, before the algorithm is going to produce the hash value, there is one requirement for this for SHA-512. What is that means? You have to add additional 128-bit and unsigned integer length field. That means to the message one additional 128-bit has to be added. Okay, in this 128-bit we are going to represent the length of the message, length of the original message. Is it clear? So what is this means the message before going to process, what we have to make means we have to add additional 128 bit to the message so that it represents the length of this original message. For example, see in this diagram, so this is a original message and this original message should be less than 2 power 128 bits. Okay, then what should be added before going entering into the algorithm? What we have to do means we have to add extra 128 bit. Okay, extra 128 bit which represents the length of this original message. And coming to this padding, what it means, so what is the requirement here? It is going to process the input message. It is going to process the input message as 1024 bit blocks. 1024-bit blocks. So the message length should be the multiple of 1024. In order to divide the message into blocks, the requirement is what it should be the multiple of 1024. Okay, in order to make the message of size equal to the multiple of 1024, we have to perform padding. Padding means adding extra bits. Padding extra bits. Okay, so how we are going to do this one means, so here what is the main requirement? We must ensure that message length is multiple of 1024 bits. Okay, 1024 bits. So what we have to do means we have to perform padding. Padding means adding a zeros, adding extra bits. So how you have to calculate how many bits we have to add means, suppose the initial length of the message, the original message length will be 2590 bits. The original message will be 2590 bits. And what is the criteria here? You have to add extra 128 bit. Okay, and the what happens? What we have to do means this one, the whatever the message, whatever may be the message must be congruent to 896 modulo 124. Okay, that is a formula we are going to use. Okay, the message length should be equal to 896 modulo 1024. Okay, so for this one, what you are going to do means, what is the length of the original message? 2590. So 2590 mod 1024. That is what the answer will be, 542 bits. So what we are going to do, we have to know how many bits. Okay, what is the formula here? So it should be congruent. It should be equal to 896. 896 modulo 1024. So you have to determine how many bits we have to part in order to make the length as equivalent to 896 modulo 124. So what we are going to do, 896 minus 542. What we got from this original message modulo 1024, it is 542. So whenever we are going to subtract, then we are going to get the answer 394. That means 394 bits has to be padded. Okay, 354. 354 bits has to be padded in order to make the message length equal to multiple of 1024. That is the main funda we are going to use. Okay, we have to make the message length should be the multiple of 1024. Why? Because means we are going to process the message in 1024 bit blocks. Okay, the algorithm is going to process the message in the form of 1024 bit blocks. So the message should be divided into blocks of equal size. And what is the size? 1024. 1024. So what we have to consider, the message should be equal to the multiple of 1024. So for that purpose, we have to perform padding. Okay, how much we have to pad means, by using this formula we can able to calculate how many bits we have to pad. Okay, for this example, for this, if the message is of 2590 bits, how many bits we have to pad? We have to pad 354 bits. 354 bits in order to make the message length equivalent to the multiple of 1024. 1024. So what is the number we got? We got 354. That is 354 bits has to be padded. For this padding, one bit should be 1. The first bit should be 1 and remaining bit should be 0. That means one bit out of 354, the first bit is 1 and remaining 353 bits are zeros. That is a padding process. That is a padding process. Okay, after padding, that is after adding the length field and after padding, the expanded message is a sequence of 124 bit blocks. 1024 bit blocks. Okay, so the message is divided into blocks of size 1024 bits and they are referred as M1, M2 up to Mn. Okay, so that the total length of the expanded message is n into 1024 bits. That is the main criteria we are going to use this is the main criteria. For that purpose only we are going to add the length field and also the padding. And after that we have to initialize the hash buffer. Okay, the next step after after adding the length field and performing the padding and dividing the message into blocks, what we have to do, we have to initialize the hash buffer. Okay, so this hash buffer is a 512 bit buffer. 512 bit buffer which is used to hold the intermediate and final results of the hash function. Okay, so the buffer can be represented at 864-bit registers. That is, now what is the total length of the buffer? 512. Okay, that is represented at 8 resistor. That is represented as 8 resistor and each resistor is of size 64 bit. That is 8 into 64 equal to 512 bits. Okay, so understand man, the hash buffer, what is the size of the hash buffer? 512. Okay, and this buffer is represented as 8 8 resistors and each resistor of size 64 bits. Each resistor of size 64 bits. Okay, and these resistors are initialized to 64-bit integers. 64-bit integers, and they are obtained by taking the first 64 bits of the fractional points of the square roots of the first 8 prime numbers. Okay, we are going to take a first 8 prime number square roots and the fractional parts of those prime number square roots of the prime numbers are taken as the 64-bit integers. That is a part of initializing the hash buffer. So then we have to process the blocks. Then we have to process the blocks. Okay. So that is the heart of the algorithm. And each block and each message and the one this 124 oh sorry 1024 bit block consists of 80 rounds. Okay. After processing all n 1024 bit blocks, we are getting the output in the nth stage. The output of the nth stage will be the final output, that is the hash value of 512 bit hash code, or we can call it as a message digest that we will show in the diagram. So how the SHA 512 will be processed means, what are the processing steps we have means, first we have to add the length field, then we have to perform padding. Okay, so why we are going to perform padding means, the message length should be equal to the multiple of 1024, so that the message can be divided into blocks. Okay, for that purpose we are going to perform padding. Okay, after performing padding, what we are going to do means, we are going to initialize the hash buffer, which is of size 512 bit, which is represented as 864-bit registers. Then after that we are going to process each block. Then the output of the last block will be the hash value, that is a hash algorithm that we will show in the diagram itself. So let's see here. So this is a message. The message is of L bits. Then we are going to add the length here 128 bits. Then remaining bits we have to part. We have to add extra zero, we have to add extra bits, so that the overall length of the message should be equal to n into 1024 bit blocks. That is, it is a multiple of 1024 bits, 1024 bits. Okay. So how is padding is done? We have already seen. So the padding procedure is, the first bit should be 1 followed by remaining zeros. Okay. Then after performing this one, we have to divide the message into blocks. We have to divide the message into blocks, and each block is of size 1024. That is the next step. Okay. Then we have to process each block separately. So what happens for each block means, the each block will be given as input a function. Okay, and we are going to initialize the hash buffer also. Then we are going to perform the addition. The addition is modulo 64 to the 2 power 64 addition. Then we are getting the 512 hash value that will be given for the second module. That will be given for the second module hash function. Like that it goes on performing. And what is the final hash code? The output of the final block, the output of the nth block is a hash code. Understood? This is the secure hash algorithm block diagram. Okay, so first we have to add the length field, then we have to we have to perform padding. After padding, we must ensure that the message should be the multiple of 1024 bits. Then the message is divided into blocks, and we are going to process each block separately. The block 1 is given to for the hash function. For this hash function, hash buffer is also one input. After processing, it is going to produce the hash code that will be given for the next block. Like that it follows. The output of the final block is a hash code. Okay, here we see the hash function takes the message, and it is going to give the fixed size output. In this is the main heart of this algorithm. In this function we are going to execute 80 rounds. 0 to 79, that we will discuss. Now we are going to discuss about processing of single 1024-bit block, single block. Okay, how the single block will be processed. Okay, so here for a single block we have 80 rounds are there. Okay, so each round takes an input of 512 buffer value. That is a hash buffer. Hash buffer is of size 512, which is represented at 864-bit registers. That is designated as A to H. These are the 864-bit registers, and it updates the contents of the buffer. Okay, and the input, and only this is not the input. Another input will be the it is a WT, a word, 64-bit value word, a 64-bit value word, which is derived from the message block. Okay, that will be given as an input. In addition to this, we are going to give another input called as a k, which is an additive constant. So all these are given as an input. Okay, after processing, it is going to produce the output. Okay, the output of the 80th round is added to the input of the first round to produce the hi, and this hi is given for the next block that we will show in the diagram. Okay, so say this is a function. Okay, in this function we have 80 rounds are there. Okay, so for 80 rounds starting from 0 to 79, for this function what is the input? Buffer is the input, which is represented as 864 bit blocks. Another input will be the word, okay, which is derived from message schedule, which is of 64 bit, and we are going to take one constant called as a k naught. Okay, k naught for the round 0 and k79 for round 79. Okay, so here it is going to process, it is going to process, and it is round 0 is producing the output of 64 bit 864 bit resistors that will be given for round 1. And round 1 is also going to take another input that is derived from message schedule. This message block is of 1024 bits, so it is going to generate a word which is of 64-bit value, and it also takes a constant. Like that, it goes on. It goes for up to 80th round. That is round 79. So the output of this round 79, is addition. Addition is performed. And what is this addition? Modulo 2 power 64 addition with the previous hash buffer. That is which is represented as 864 bit resistors, and we are going to get the hash code, we are going to get the hash code hi, which will be given as input for the next block, like that it follows up to the nth block. So whatever we get at the end of the nth block is a final output, that is a 512-bit hash code. I hope it is clear. Okay, we will see the behavior. So first, there is no hash buffer. We are just going to initialize, that is h naught, and we are going to initialization vector will be taken. Then how h1 is obtained means you are going to perform the addition of 64, that is modulo 2 power 64 addition of what we are going to do, this hi minus 1 previous hash buffer and the output of the last round, so that we are getting hi. And what is the end at the end of the nth round hash code is the message digest. That is the behavior of this SHA algorithm. And in each round, what happens in each round? Okay, what happens in each round? You just take out these ones. Okay, we'll show in the diagram. Okay, now this is round 0, and round 0 output will be given for round 1. So these are the transformations going on. Okay, so WT is a 64-bit word derived from the current 1024-bit input block, and KT is a 64-bit additive constant, and this is the addition modulo 2 power 64. Okay, so these are the 864-bit resistors, how they are transformed for the next round. Okay, this A resistor becomes B resistor in the second round. Okay, for the next round, and this A, yeah, this calculations will be done. A, B, C are given to a major function, so that will be added to the summation of A, and it becomes A. Like that, some calculations are there, and this is a round function. The final will be the 512 bits only. So again, this processing will be done in next round. Finally, we are going to perform addition of the previous hash buffer, so that we are getting the hash buffer that can be given for the next round. So, and how this word can be generated means like this. So one, it is a 64-bit block. It is a 64-bit value. So from 1024-bit block, we can able to generate 16 words. After 16 words, we have to generate like this. Okay, by using this formula. By using this formula, we are going to generate the next. What we have to do, we have to generate 80 words. Okay, but from 1024 bit block, we can able to generate only 16 words, and remaining words can be generated by using this form. By using this formula, we can able to generate the next words. Okay, that will be given as an input. Okay, see. So this is a 1024 bit block. From this 1024 bit block, we can generate 16 words. We can generate 16 words. Each word is of 64 bits. From word 16, that is 0 to 15, we can able to directly generate from directly. We can directly derive from this message block. Okay, but for 16th word, what we have to do means we have to take this formula. That means we have to take W naught, then W1, W9 and W14. Then we have to perform sigma naught and sigma 1 operations, and lastly they must be added in order to produce W16. Like that we are going to generate up to W79. So this material is prepared by using these references, and if you have any queries, you can send your queries to this form. Hope you understand. Thank you.